ladies and gentlemen. Welcome to attend this session. My name is Pei Zhang. I am a quality engineer from Red Hat. Today I'm going to share configuring and benchmarking Open vSwitch, DPDK, and the vhost-user. This is a typical NIV solution. In today's talk, first I will give a simple background introduction of the NIV. I will explain why the network performance is important in the virtualization environment. And then I will share the configurations. I will explain each component, how they improve the performance. Next, I will show how to get better performance based on the user's different performance requirements. Last, I will show our testing results with this configuration. NIV, the full name is Network Function Virtualization. It's a variety of the network appliance will be replaced by the virtualization and the software, which means the network function, they will be not limited to the specific hardware. It will be implemented as the software in the virtualization environment. This is the NIV architecture proposed by the European Telecommunication Standard Institute. It has mainly 4 constituents. The light bottom is the NIV infrastructure. In this layer, the hardware resources are virtualized as virtual resources, including the virtual computer resource, network resource, and the storage resource. So it provides these resources to the upper layer, the virtual network function layer. The virtual network function, they develop their softwares in the virtual machines. And the red part is the NIV manager and orchestrator. It covers the management and the lifecycle management of the hardware resources and the virtual resources. And it also covers the lifecycle management and orchestrator of the VNFs. The top layer is users' operating support system. So this architecture, it's an ecosystem. Different vendors can all involved in, also including the network function vendors. So when they develop their software in the virtual machines, as the telecommunication, they have strict requirements for such as the fault management and the security management, also the network performance management, including the latency and throughput. The network performance should be ensured at acceptable level. So one replace the software with the hardware with software, the network should also be ensured. So as they develop the software in the virtual machines, so that's why the virtual machines should be able to provide good basic network performance. So this is what we are talking about, provide good network performance in the NIV infrastructure. This is a configuration. Open vSwitch and the QEMU VM running over the Real 7 platform. The Open vSwitch is accelerated by the DPDK. The VM and Open vSwitch communicates by the vhost-user protocol. Also, in the host, the Linux network driver is replaced by the user space driver VFL. So let's say how each component improve the network performance. Let's say DPDK first. DPDK is a data plan development kit. It's a set of libraries and drivers for fast packet processing. So it has these are its features. the polling mode drivers. So polling mode means the CPU constantly check the status of the network ports, no matter it's busy or idle. So the poll mode drivers, it will polling the network ports constantly. So each poll mode threading will cost 100% of the CPU resource. And also the DPDK supports the multi-PMD threadings. Another feature is it uses huge page. The default huge page size is 4 kilobytes, and the huge page size has 2 megabytes and 1 gigabyte. As huge page never swap out of memory, it has lower TLB miss. That's why the performance can be improved. Another feature is DPDK handles the packets in the user space. It's not providing the layer 3 network packets. It supports the layer 2 network packets. So let's compare the standard Linux kernel driver and the DPDK. The standard Linux with standard Linux kernel driver, when the network arrives at the network card, it will through the Linux network stack, and the user's application get this package by system calls and copies the memory from the kernel space to the user space. As the DPDK, it uses the user space driver, so the Linux network stack is bypassed, as the Linux network stack is designed for more common network applications. It supports the protocols from the different network layers. So in DPDK, it's the user space driver. This stack is bypassed, and also the user space application can directly visit the physical network. So there is no the system calls and no memory copy. So that's why the DPDK in the user space, it can improve the network performance. So the DPDK has supported the vhost-user backend. Vhost-user is a QEMU feature. It allows the VM to the virtual machines to share its memory with another user space applications on the same host. It's an improvement from the VirtualNet to the vhost and to the vhost-user. So the vhost-user, it's a server-client mode. It communicates by the unit domain socket, and the shared file descriptor is in this socket. So when the VM acts as the server mode, and the DPDK can act as the client mode, and vice versa. So the Open vSwitch has support the DPDK and vhost-user. I'm not talking a lot about the Open vSwitch. It's complicated. I only talk about the performance-related part. As the standard OVS, the data path is in the kernel space. Now they support the DPDK and vhost-user. They have added the user space data path, the netDEV. So it means when the package is received, they will be handled in the user space. So let's KVMRT. For some VNFs, they may be latency sensitive. So that's why the KVMRT may be required. I will talk the results later. So let's do a summary. With this configuration, all the packets, they are handled in the user space. And this configuration is using the polling mode drivers, and more cores can be used and as 100% cost 100% of the resource. Another is the huge page is used in this configuration. Also, I'd like to highlight another two points is CPU isolation and CPU pin. So in this configuration, either the CPU is used by the Open vSwitch or used by the VM. These CPUs should be isolated, which means they will be, for the isolated CPUs, they will not be used until they are explicitly set. So when we isolate a group of cores, we pinned the threading to the dedicated CPUs. Also, there should be no overlap. So the CPU pinned to the Open vSwitch should not be overlapped with the CPU pinned to the VM. Another point is the strict NUMA policy. If the NUMA host at least has 2 NUMA nodes, so the Open vSwitch and the VM should use the CPUs and memories in the same NUMA node with the network device. Otherwise, the network performance will be lower. So this is some details of the config. This is a vhost-user. Vhost-user, the memory must be set shared. And when the VM acts as the vhost-user server, it will create the vhost-user socket. And the Open vSwitch must use the same vhost-user socket. So the OVS VSCTL is a user interface of the Open vSwitch. It can query and set up some executions of the Open vSwitch. Which page needs the CPU support and the kernel support. So this is a flag for support the 1 GB which page. Also, we need to add the default which page size to the kernel line. This is how the which page is used in the XM file of the virtual machines. This is isolated cores. We isolate the cores by adding the ISO to the kernel line, and also actually in our testing, we isolate the cores by the tuned. In the non-real-time system, we isolate cores by using the CPU partitioning. In the real time, we use in host we use the tuned NIV host, and in the guest we use the tuned NIV guest. Also, besides the isolated cores, the tuned will add some options. These options they are time sticks, timer, or something like that. So in order to improve the performance. NUMA policy. First, we need to check the physical network where it's located. We check this by the hardware log. And in this example, it's located in the NUMA node 1. So then when we boot the VM, we should use the CPU and the memory in NUMA node 1. And we band all the PMDs of the Open vSwitch in the NUMA node 1. Also, there is no overlap. In this example, I used the 4 cores for the Open vSwitch. This is a KVMRT. Actually, with KVMRT, we didn't cost more resources. Just the configuration is different. This is a VM. We add all the CPUs to the FIFO1 priority. And we need to install the kernel RT packages and the kernel RT KVM packages, and also use the FIFO1 priority to all the PMD threads. This is our testing topology. We have 2 hosts connected back to back. The Mongen running on one host, and the Open vSwitch running on another host. The Mongen is running over the DPDK. It generates packets from one port and receives it back from another port. So this is how we measure the throughput and the latency. The Open vSwitch, we created 4 ports, 2 DPDK ports and 2 vhost-user ports. The 2 DPDK ports, it communicates between the external and the host. And the vhost-user communicates between the VM and the host. So the whole packet flow is, it receives the packet from DPDK. And in the open DPDK port, and in the open vSwitch, we add a flow between the DPDK port and the vhost-user port. And then it forwards the packets to the vhost-user port. And then the guest can receive the packets from the vhost-user port. So this is our testing topology. And also, we totally have 6 ports. The open vSwitch has 4 ports, 2 DPDK ports and 2 vhost-user ports. So per port, we need to bind a dedicated core, which means the open vSwitch will cost at least 4 cores. And each cost, all of them cost 100%. And the VM costs 2 cores at 100%. So in this configuration, we at least need 6 CPU resources. I will show the results later. So how to improve, that's I explained the correct configuration. So how to improve the network performance, as some may need higher throughput, some may need lower latency, and some may need 0 packet loss. So for higher throughput, we support the multiqueue. The open vSwitch and the VM also need to set multiqueue. Use also the CPU partition. With CPU partitioning, we can reach 0 packet loss and lower L2 network latency. Also, I will show also with KVMRT. KVMRT can provide the lower latency. Actually, in order to make the difference, I call this latency to the cyclic test latency. I will explain more later. This is multiqueue, our testing topology. It's very similar to the former one. The different is the lines are doubled. So for the each port we bind dedicated cores to each port. So for each queue, we also need to bind the dedicated cores to per queue per port. So for the 2 queues, we need at least 12 cores. And this cores should be in the same NUMA node with network devices. This is a configuration. Configure it with the open vSwitch. Set the PMD dedicated cores and set the RX queues of the DPDK port. This below is the VM vhost-user 2 queues. So this is the testing results. With 2 queues, the throughput value is much higher than the single queue. It can reach we are testing with a 64-byte packet size. It can reach the 70% of the line rate. We are testing with a 10 gigabyte network cards. Actually, this result can reach the when we testing with the bare metal, the throughput is also this value. So this is the maxi throughput we can reach. With CPU partitioning and without CPU partitioning. With CPU partitioning, we can reach the 0 packet loss, and the network latency is lower. So we test the L2 network latency by the time span between receive time and send time. This is the cyclic test. We didn't compare the KVMRT with the CPU partitioning. This is because their testing results is similar. This is because in our testing, the test PMD is a simple forwarding application. So, but in the real VNFs, they may be complicated applications, and they have more complicated operations. So that's why I think I still need to put the KVMRT latency testing here. I mean, this testing is not a test with the DPDK and the Open vSwitch. It's just the KVMRT. And also I compared it with the CPU partitioning. The latency value is lower. It's the threshold in our testing is set to 20 microsecond. So this is the KVMRT. Now this is the results with the configurations. So that's all. Any questions? Okay.
Kind of VM did you use on the Linux? Windows?
Linux, only Linux.
No Windows.
No Windows. Yeah.
Which you?
We use 10 gigabytes, the X540. Yeah, it's 10 gigabytes network card. Okay. So seems no questions. Okay, please.
Did any testing with faster cards and NUMA, let's say 40G cards and NUMA?
Excuse me, could you?
Have you done any testing with faster NICs, like with a 40G card and NUMA or some other packet generator?
Seems the Mugen doesn't support the 40 gigabyte network card, so currently maybe our other teams, our network teams, they are covering this the 40 gigabyte network card. I didn't cover it. Yeah. Okay. So if you are interested in it, maybe you can left your email and I can let them to transfer more info to you. Yeah. Okay. So thank you for attending.